For my project, I studied an optomechanical sensing technique which could be used to search for axion-like particles clustered into boson stars. As it stands currently, there is significant evidence for the existence of dark matter, but no specific particles have been detected yet. In recent years, the focus of dark matter research has shifted to ultralight and axion-like candidates, since heavier particles have not yet been detected. One particular technique which would increase detection reach is optomechanical sensing. Essentially, this technique uses a mechanical force sensor coupled to an interferometer, as you can see in the picture. When a dark matter wave interacts with the sensor, it causes the sensor to move, leading to a phase shift in the optical cavity, which we can pick up on the interferometer. Previous works have shown that this type of detector offers many advantages, especially when scaled into an array. We assume that ALPs interact with the standard model via a Yukawa coupling to neutrons, which has the effect of modulating the mass of a particle. As a boson star moves across the sensor, it causes the center of mass of the sensor to shift towards the boson star's center of mass, causing the sensor to move. Formally, we assume that coupling is of the form shown here, where y is a coupling constant. And we assume that the dark matter field in the non-relativistic limit is of the form in this equation. Since the Gross-Pitevsky equation describing the star is Galilean invariant, the field psi must obey this transformation law. And then the above equations imply that the dark matter field in the boson star is of the form shown here. By noticing that the coupling term behaves like a mass term in the Dirac-Lagrangian, we determine the force on the sensor due to an ALP is of the form shown here. To model the boson stars, we assume that they can be described using an energy functional of the form shown here, where Vg is the self-gravity, which is determined from the Poisson equation, and lambda is the self-interaction between the bosons. To determine the wave function of the boson star, we use a variational technique with the variational ansatz of the form shown here. By minimizing the energy functional with respect to sigma d, we determine that sigma d is equal to this equation here, and then we substitute sigma d back into our ansatz to determine our approximate wave function. And then using this wave function, we can evaluate for the central density of the boson star, which is equal to this equation. Now, to verify that this estimate for dark matter density is consistent with experimental results, we compare the density of the boson star ansatz with some observational upper limits on the matter density in our solar system. We determine that the upper limit on boson star density for a boson star centered around the Sun is approximately equal to 5 times 10 to the 4th GeV per centimeter cubed. Compared to a diffuse dark matter field with density equal to the local dark matter density of 0.3 GeV per centimeter cubed, a boson star centered around the Sun has a much higher density. Since the force on the sensor is proportional to the square root of the dark matter density, we hypothesize that the signal we could observe for dark matter in a boson star is going to be much higher than for a diffuse field. To determine the collision rate for a star coming from outside our solar system, we assume that the collision cross-section is equal to this equation here, where our target is equal to the radius of the Earth, and R99 is approximately equal to the radius in which 99% of the mass in the boson star is contained. By assuming that the mean free path is given by this equation, and the number density is given by this equation, we can determine that the collision frequency is equal to this equation here. And then rewriting frequency in terms of central density gives us this equation here. The observed helium abundance in our universe also constrains the allowable coupling values. If we assume that the neutron to proton ratio is given by this equation here, where Q is the neutron proton mass difference, and the change in neutron proton mass difference due to ALP coupling to the standard model is given by this equation, and the mass fraction of helium is given by this equation, we can determine that the change in mass fraction due to ALP coupling to the standard model is given by this equation. And then since helium abundance is known within 10% accuracy, we can determine a numerical constraint on coupling, which is given by this equation, where mass is measured in eV. We also look at constraints on coupling from fifth force experiments. Comparing fifth force constraints to constraints from BBN shows that fifth force experiments actually place tighter constraints on coupling than BBN across the parameter space we're looking at. As you can see in this graph here, this blue region represents coupling values and mass values, which have already been ruled out by fifth force experiments. And then this red line here represents the smallest possible mass and coupling value, the smallest possible coupling values we could observe for a particular mass. So then this white space in between the red line and the blue line represents the available parameter space which this experiment would be sensitive to. So in conclusion, we determined that this type of experiment would be useful for searching for axion-like particles in boson stars, for stars centered around the sun, and for stars in outer space. To finalize calculations in this project, we still need to finish scanning over the entire parameter space to determine the detection reach. For the calculation above, I used a particular value for self-coupling and for the number of particles in the star. But by changing this value, we would get a different limit on the smallest observable coupling, which could change the parameter space that we would be looking in.